This is going to be a small lecture, not very long, regarding the difference in these problems that you're working here for the review over whether or not to have something in the numerator or the denominator. What you're going to find is that lengths operate a little bit differently than the dose rates. And let me try to rewrite that just a little bit more clearly. So when it comes to lengths, we're going to be looking at something comparable here to similar triangles. What do we mean by that? Well, if we have two triangles here that are sharing the same angle, then we need to look at the proportions of these lengths. I'm going to call that D. Okay, so when they're sharing the same angle there, and particularly when they're supposed to be right triangles, which this is a right triangle, even though it doesn't look like it, what you're going to find here is that for the similar triangles, the ratio of A to B is going to be the same as C is to D. And what that means is that the opposite side of these similar triangles from this angle are always going to be in the numerator, and the other leg here is going to be down here at the bottom. So when you look at both fractions, the opposite side here is on top, the opposite side here is on top, and what's on bottom is the respective leg of each one of those triangles. So that's pretty much how that's going to set up. That's why when we're looking at things, that change, we're looking at a field size, say 10 cm in one dimension, and we're looking at that, say at an 80 cm SSD, and say we want to know what it is at 100, then we might, in this particular case, say A is equal to 10, B is equal to 80, because at 80 SSD, then this length right here is going to be equal to 10. And let's say we take B and we change it into D, and so we make that equal to 100. Then what happens here to C? Or what is the value of C? We plug all that information in. So we get 10 divided by 80 is equal to C divided by 100. Solving that for C, we end up with 100 times 10 divided by 80. So that leaves us 8. So you go through, you do the calculations here, and you can figure out exactly what C is. And C should be bigger than 10. And in this particular case, it is. It's 100 divided by 8. So that's how the lengths work in this particular case. They work off similar triangles. Dose rates, on the other hand, operate a little differently. So say you've got a source here, and it's emitting radiation. Well, the amount of radiation that you would see here is going to be different than what you would see as things spread out this way. So what you're going to see here from this particular source is going to be more concentrated than what you would see here, because by this time, or at this distance away, you're looking at these rays spreading out. This doesn't look quite so spread out, but maybe if we do something like that and something like this, then you can see how spread out they become. So that's why in this particular case, when we're, say, looking at a dose rate of 250 at, let's see, erase some things. Go through and do this again. So let's say you've got dose rate of 250 centigrade per minute at, oh, I don't know, 80 cm, let's say. So what is the dose rate at 100 cm SSD? Well, what do you end up doing in this particular case? Well, in this particular case, in many other cases, what you're going to find is that, let's say this was at 80, and we're looking at around 100 right here, SSD. The dose rate here, since it's further away from this, should be less. And it's going to be less by an inverse square amount. So let's say we have our dose rate here, 250 centigrade, and we don't know what it is over here, so I'm just going to call it X because I have no idea what it is. We don't follow the same similar triangle argument where, you know, one leg, opposite leg over adjacent leg is the same as the opposite leg over the adjacent leg over here. Rather, instead, over here, we need something that is going to tell us that the dose rate here is going to be smaller than what it is here, because that's what we observe. So in order for it to be smaller, rather than say 100 over 80, we're going to have 180 over 100 because it works according to the inverse square law. So whatever's here to whatever's here is going to be flipped around. In other words, we need to have a lower dose rate here. Now, unfortunately, I think I wrote that incorrectly. Let's try that again. There we go. We know that the dose rate here, which I'm going to call X, should be lower than what it is here. So the ratio of that over 250 should end up being less than 1. That's why when we look at this, we want to make sure that our ratio here is less than 1. And the way you do that is, rather than put, say, 80 down here in the denominator at the same place where the 250 is, it should rather be in the opposite position. So when we go through and we solve this, we would find out that X is equal to 250 centigrade per minute times the result of 80 divided by 100 squared. So because this is obeying the inverse square law, basically what it's saying is the further away we get from the source, the smaller this number should be. And the only way that's going to happen is if we end up with a smaller number here, or a number less than 1 to multiply by the 250 when we do the cross multiplication. If, however, we were going from 100 to 80, we would find out that the dose rate is becoming larger because we're getting closer to the source, which means that more of these rays over here are going to be collected into the same space as what we would see here. Our dose rate's going to be higher. So if it were, say, 250 here and we didn't know what it is here, but we wanted to know it, we would reverse not only this, but also this as well. So the 250 would go here, the 80 would go here, 100 would go here, and then the X would go here. So that's just a small lecture there. I hope that helps clarify things just a little bit.